Okay, this video is going to look at condensed structures. So on this piece of paper, I have what we call Kukuli structures. And Kukuli structures are ones where every atom, every bond is shown. And they're really cumbersome and annoying, especially in organic chemistry when a lot of times we're dealing with carbon backbones. A lot of these drawings take a lot of work, and there's some shorthand ways to do it. And the first way is to try to condense these structures, and we actually just call them condensed structures. And instead of showing every single bond like what we do in the Kukuli structure, in the condensed structures we sort of simplify it a little bit. So let's take this molecule here. This is ethane. It's a really simple molecule. Now, instead of drawing every single carbon-hydrogen bond, we try to reduce those carbon-hydrogen bonds, condense them down into units. And so we're going to think of each carbon in this structure as possessing a unit. And this carbon is going to be a CH3 unit, and so is this one, a CH3. So instead of drawing every single carbon-hydrogen bond, what we can do is call this CH3, CH3. Now we're assuming that the carbons are bound to each other because we're in organic chemistry and we usually have carbon-based backbones. Now this could also be an H3C unit, okay, but most of the time we call them CH3s. Sometimes you might see a condensed structure for ethane that looks like that. That's also okay. Okay, again, we're making an assumption that the carbons are bound together in that molecule. Okay, let's move on to the next one. This one's more complicated because it's a branched molecule. How do we show these branches in there? Well, again, we kind of go carbon by carbon and try to define the units that are present in this molecule. So here we have a CH3 right at the end. Here, what do we have? Well, really, we've just got a CH, right? Now, coming off of that in a branch, I'm going to define this CH3 unit, and in order to designate that it's coming off of this one in a branch pattern, one option you have is to put it in parentheses, CH3, okay? And then finally, we have another CH3 at the end. This is just a fine way of showing this branching by indicating this with parentheses. Sometimes I like to do it another way. I just show the branch, and this is fine. So I combine a Kukuli structure with a condensed structure, and I say, well, I got a CH3, I've got a CH3 in my main unit, and then I'm just going to show you. Look, I've got a CH3 branching off there. Either one of these is fine. Okay. Here's another one with more complicated branching right at the end here. And so we can say this molecule starts with a CH3 unit, then it goes to a CH2 unit, and then we've got just a C unit here. There's no hydrogens directly attached to that carbon, but we have 3 CH3 units attached to it. And so again, I can indicate that we have some sort of branching by putting those in parentheses, CH3, 3. Or I could do something where I indicate that branching with bonds, right? CH3, CH3, CH3. Again, any of these options is a whole lot better than drawing the whole thing out. Here's a next molecule. It's complicated a little bit because we have a double bond in there. Okay. Now, we assume in organic that each carbon is going to have 4 bonds, and that's going to allow us to do these condensed structures without too much of a shortcut. So let's try. We've got a CH3 unit at the beginning. We have a CH unit. We have another CH unit, and then ending in a CH3. This is fine as a condensed structure for this molecule that has a carbon-carbon double bond, also known as an alkene. You are supposed to know that each carbon has to have 4 bonds associated with it. So if these carbons don't have enough hydrogens, then there must be some double bonds in there, and you should be able to figure out how many. You can indicate the double bonds in here if you want to be nice, but you don't have to. So sometimes condensed structures of alkenes can be shown like this. But they don't have to show that double bond there. Okay. The next one we have down here has some non-carbon containing atoms in it, and in the condensed structure we have to deal with those also. So this one starts pretty normally, CH3. Then what do we have here? Well, it's a CO2, right? And so we put CO2, and then at the very end of this is an H. What you'll find is the CO2, again, you have to understand that this carbon has to have 4 bonds associated with it. So if one bond is with this carbon, then we have to have 3 more bonds with the oxygens. So one's going to be a double bond, one's going to be a single bond, and then this hydrogen at the end. This is a real common condensed structure indication of this type of pattern, and we'll see that more as we get into these functional groups like carboxylic acids. Okay, let's do this next one here. We got a chlorine at the end. We got to indicate that as a chlorine. We've got a CH group next. Another CH group. I'm going to be mean and not put that double bond there. Then we have some sort of branching occurring here. Now, when it's complicated like this, we've got branches that have 2 separate units associated with it. I suggest using this type of nomenclature. We indicate we've got a bond here that goes to a CH3, a bond here that goes to an OCH3. Okay. Sometimes you'll see the lone pairs indicated, sometimes they'll be absent. Okay, the last one here is a cyclic molecule, and these are common in organic chemistry. Again, it takes a lot of time to draw this out in Kukuli form. In condensed structures of cyclic molecules, you really have to show how these carbons are bound together. And so what I'm going to do is just put each of these carbons as a CH2 unit, and I'm going to show how they are connected in a cyclopentane or 5-membered ring structure. That's a good condensed structure for this cyclopentane molecule.